Okay, today we're going to prove this integral which states that the area from theta 1 to theta 2, so in other words the area of the entire interval of the polar curve is 1/2 times the integral from theta 1 to theta 2 of f of theta squared with respect to theta. So to start, we have to split something up into n pieces. In this case, it's this angle. So we can split this angle to finite pieces, but we're going to take the limit as n approaches infinity. Unfortunately, I do not have the capability to draw infinite of something, so be patient enough to imagine this as infinity. So the angle of one of these pieces, the angle of this is theta 2 minus theta 1 over n, limit as n approaches infinity. The length of this piece is f of theta 1, and the length of this piece is f of theta 1 plus this angle, so f of theta 1 plus theta 2 minus theta 1 over n. But limit as n approaches infinity, this term becomes 0, so these are practically equal when n is infinity, or at least approaches infinity. So we can treat this entire arc right here as arc of a circle. So in other words, if it can be treated as an arc of a circle, it has the same area as the arc of a circle. And the formula for arc of a circle is the angle over 2 times the radius squared. So the angle in this case is theta 2 minus theta 1 over n divided by 2 times f of theta 1 squared. Now the area of the next piece is going to be the same right here. The angle is going to be the same. The length of this, however, is going to be equal to this, and this is going to have an extra theta 2 minus theta 1 over n. So it's going to look like this. Going to have the same angle. So you're pretty much having the notion of next. So these two are the same thing. They represent the same thing. They're adjacent to each other. So you're going like next piece right here. So the length of this piece is f of theta 1 plus 2 of this. So 2 theta 2 minus theta 1 over n. So in other words, you can treat it the same as n goes to infinity. The area of this is theta 2 minus theta 1 over 2n f of theta 1 plus theta 2 minus theta 1 over n squared plus theta 2 minus theta 1 over 2n times f of theta 1 plus 2 theta 2 minus theta 1 over n squared, and so on all the way up to the nth piece. So you can rewrite this entire thing as a series. So this is the series of f of theta 1 plus k theta 2 minus theta 1 for n times theta 2 minus theta 1 over n. And I factor out the 1/2 right here over here. So it's from k equals to 0 all the way up to n, limit as n goes to infinity. So we can rewrite this as integral. Or first we're going to rewrite this as a Riemann sum, then as integral. So we're going to do this using my definition of Riemann sum, so which is states k equals to 1 to n, limit as n goes to infinity of g of theta. I'm just using a different function here not to confuse these. Or in this case, g of a plus b minus a over n times k times b minus a over n is equal to integral from b to a, or a to b, of g of x dx. So you can just define this in terms of this. So A is just equal to theta 1, B is equal to theta 2, and then this is just this squared. Just forgot to write that. Yeah. So these two are equal, so you can write this as integral. So in this case, it's not g of x, it's f of theta squared from A to B. F of theta squared with respect to theta, which is what we stated before. So just draw a box around it. Check mark, smiley face, and we're done.